Right, Gary, the
Okay, so realizing the power of systems thinking in technical management. Okay, so this is essentially the content I'm going to take you through. There's an introductory part where I'll talk about some context setting. I'll talk about systems thinking in project management, and I'll explain the relationship there to systems engineering. Um, there's a part on understanding the project start and the assumptions that we make and the impact of those assumptions. I'll also be looking at organizational complexity and dysfunction, the impact of that, and how through the power of technical management we can essentially bring some order to chaos and make things more systemic. I have some bonus slides on developing systems knowledge and analysis of PM principles and also SE principles. I won't go through that content, but the slides for that content will be available after the presentation for people to look at. So first of all, I'm going to look at the impact of size, complexity, and confusion, and the impact of that on projects. I'm going to lean on two really useful pieces of work. One is the chaos report from the Standish Group, and what has been expressed there is that over 5 decades of cumulative data analysis on very large IT projects since the 1990s. The results are essentially, 90% of those projects fail utterly, 46% are challenged, and only 35% are deemed successful. And essentially, that has not changed over the last 30 years. There's also this really great book by Flyberg, and I'd recommend that to everybody. He's been assembling a database on mega projects, 16,000 projects, and he's found that a staggering 91.5% of projects go over budget. And worse, less than 1% of projects are completed on time and on schedule and actually deliver the benefits promised. So there's this relationship between large projects going over budget, not succeeding, and there's a correlation with complexity. The other really important and useful piece of work has come through our alliance with PMI and the MIT. And this survey of project managers and chief engineers, which was undertaken within that alliance, they've identified that there is an unproductive tension between the two disciplines, which it's not helpful in our programs and projects. And one of the leading causes of tension is a lack of integrated planning, and things like authority not clearly defined. One of the outcomes of that alliance was also a guide to lean enablers in managing engineering programs. And there's this really nice diagram in that work which shows PM processes and SE processes and how together those two things lead to better solutions, because both of these roles are absolutely key when we're delivering complex programs. But what I'm going to suggest to you is there's actually this intersection between them where there's the possibility that neither role really takes on that responsibility, and I think that gap is what we're starting to call technical management. It's that bridge between the two. The technical manager understands the project manager, and the technical manager also understands the SE processes. And that level of technical management is really necessary when we're dealing with complexity. And this is one of the subjects of the PM SE integration working group. So bridging that gap, so the chief engineers take responsibility and accountability for the technical aspects, and the program manager takes accountability for the programmatic aspects. But in order to successfully manage both aspects, there's this area in between where the two disciplines need to cooperate. And this is where I think technical management comes into play. Part and parcel of this overall scenario is the importance of systems thinking, because systems thinking is believed to be a way of increasing our ability to manage complexity. And I'll draw on two articles here that I found which are again really useful. Systems thinking, innovation, project management, a match that works, and also systems thinking, taming complexity in project management. Um, the key finding is that systems thinking methods provide the flexibility to manage innovation, complexity, and uncertainty in innovation programs more successfully. But on the other side, surprisingly, project managers do not seem to use simple systems thinking tools, even though these provide unique benefits in framing and solving problems that arise from multiple perspectives and relationships. Another nice piece of work has come from the Association of Project Management in the UK. And what they've been doing is they've been looking at the relationship between, again, systems thinking and complexity. And the other thing that they've done is in this white paper is they've identified a number of systems thinking tools, including things like failure mode and effects analysis, for instance. And what they've done, they've looked at the application of these tools across the life cycle, so where these tools provide the most benefit. So what is systems thinking? So systems thinking is something that I've been looking at for quite a while now, and myself and Bridget Daniel Allegro did some work on this, and what our perspective on this is that the systems thinking is what you have to do when you're faced with the inexplicable, those things that you just don't understand, they're beyond your comprehension. Systems thinking changes the way you think and improves your understanding. And a key aspect of this is changing your attitude about things. And this quote from Captain Jack Sparrow is really nice. The problem is not the problem. The problem is your attitude about the problem. Do you understand? And the subject of systems thinking is essentially everything, because systems are everywhere and everything. And this is the subject of system science. So systems thinking is from one perspective, essentially applied system science. So when you do systems thinking, ideally, you are using your systems thinking in the context of an understanding about the nature of systems. To explain a little bit about my background and where I'm coming from, because that's obviously influenced very much the way I approach things. Originally, I was an analytical chemist, and then I moved from analytical chemistry into software engineering, systems design, and I inevitably went into team leadership and engineering project management and commercial project management. And I don't mention this very often, but actually, in my background, I've got 20 years of project management experience. But I found the light and came back to engineering and systems engineering. I've contributed to the book Integrating Project Management and Systems Engineering as a reviewer. I'm an INCOSE ESEP. I've also applied systems thinking and systems approaches outside of engineering in the biological context. I've published a number of papers on things like cancer and inflammation, applying a systems perspective. And as Andy mentioned, I've had a lot of associations with the International Society for System Sciences. So there was a piece of work that Bridget and I did a few years ago, and some of you may remember a little booklet that we handed out, which was exploring the landscape, exploring the landscape of systems. And within that booklet, we utilized something called the systems tree. And this contains heuristics in terms of how to do systems thinking. The branches of the tree represent essentially the attitudes of the systems thinker. So things like imagining scenarios, anticipating the effects, looking for influential factors, etc. So these are the kind of things that the systems thinker does in terms of their attitudes. But the roots of the tree are the things that the systems thinker thinks about. And many of these things that you find in the roots are the subject of, for instance, of our model-based systems engineering. Cycles, functions, inputs, outputs, the needs, the hierarchies, all of that kind of stuff. And there's also what we defined as an anti-tree, and the anti-tree is traps in thinking, and also unfounded concepts, because nothing is truly useless. And indeed, there's no such thing as nothing, really. Even nothing is something. Now, one of the things that we looked at in the roots of the tree is cycles and the importance of looking at the overall life cycle. And here we have a typical project life cycle going from concept, feasibility, through the planning, through the development, etc., etc. And there's obviously an investment at the beginning, but the whole point of delivering a project is that there's benefits, and the benefits should outweigh the costs. Now, when does systems thinking actually start, and does systems thinking actually end? And I want to draw attention to the estimating funnel as we go through those early phases. Our degree of uncertainty reduces over time, where we get a better and better understanding of what the project is and how it's going to be delivered. And eventually we get to a point where we have a really good idea of the time, cost, quality triangle. And that from that point on, you're essentially in implementation. But there's an awful lot of systems thinking which takes place before potentially traditionally the project starts, because the project manager is traditionally responsible for time, quality, and cost. But actually, there's this whole set of phases prior to project startup where there's a lot of systems engineering and a lot of systems thinking which is needed. And there's been some uncertainty on when does the project start, and when the importance of that, because when we look at the overall life cycle, and this is one potential scenario. You have that proposal phase, which is under the responsibility of sales and marketing, where you're doing the conceptualization, you're working out what the solution, what the problem is, and what the solution needs to be, and you make it. If there's going to be a contract, you often have a firm commitment in terms of the cost of the actual thing that you're going to be delivering. And there's this handover from the proposal phase to the commercial to the realization phase, where the project manager comes on board, and all of a sudden we discover that the time, cost, quality triangle is very much not the one that we imagined it to be. There's a big surprise, and this continues from the realization phase to the operational phase. The project manager has a burden of delivering a project to time, cost, and quality again, and they want to get rid of that project as soon as they possibly can. Yeah, and sometimes what happens is when you deliver the solution, it's not fit for use, and we've seen many examples of this. So the thing I'm trying to get across is where does systems thinking start and end? And from a technical perspective, should we not be considering the overall life cycle, which of course from systems engineering perspective, we know that that's really important. Now, the impact of those misunderstandings, those assumptions that are made, we have a pretty good understanding of the impact of those now using COSISMO as a tool. So some of you may be familiar with COSISMO, the work of Ricardo and others. It's a cost model which was developed with the support of Boeing, Lockheed Martin, and several others. And what they were doing was they were looking at the factors which lead to the amount of systems engineering effort that is needed. Now, instead of using COSISMO as a way of estimating the amount of effort needed, we've been using COSISMO in the context of the SEPM working group to look at the cost of those assumptions. So, for instance, we've got two examples of projects here. We've got one project and the assumptions which were taken prior to contract, which are in red, and the actual situation that was found. And Project A is an example of a pretty good project. The thing which seemed to make the difference between what was expected to be costed and the actual cost was this slight difference in architectural understanding. You know, when you multiply up all of these factors together, COSISMO would predict a multiplication of 1.23 times the amount of effort needed based on what was originally assumed prior to contract. And the chief engineer who carried out the survey and provided the results for this explained that on their program, the architectural understanding, which was originally expected to be high, turned out to be nominal, and then this led to that increase in effort. Project B is a situation which was much more serious. Project D is where the requirements understanding was assumed to be high, but actually it turned out to be low. And when you multiply all of these different factors up, it leads to a multiplication of 5.33 times. And indeed, this correlated with a 500% increase in costs. And this kind of analysis was done in several workshops across many programs and projects, and the correlation turned out to be pretty good in all of those cases. So what this is explaining is the vital importance of doing that work prior to contract to understand where you are, so that your level of systems engineering and engineering effort is indeed tallying with the reality of the situation. Because these understanding phases, prior to the point where you have a fixed time, cost, quality triangle, is really key. You know, the conceptualization, requirements engineering, systems design, the lower level design, which then results in your item requirements, for instance. This is vitally important. You know, during those early phases, exploration, thinking, testing assumptions, iterating in planning, thinking again, this is where we do the most of our work to resolve cost of non-quality and to ensure that we're doing the right things at the right time in the right way. Because when you don't do it the right way, you end up with curves that look like this. This is what technical debt looks like. You know, prior to contract, if you don't do the right work at the right time, you are essentially taking out a loan. And the severity of that loan can be as bad as a loan shark. And you end up with a curve that looks like this. And those kind of projects can be, you know, very, very painful. All I'm trying to emphasize here is the importance of systems thinking, of planning, defining architectures, understanding the problems, defining solutions, doing all of those things before you agree to a fixed cost is really important. And many of our customers are getting wise to this, and they now have phases where we do you know, where that early work is actually funded, because that early work is absolutely needed. The other thing which can seriously impact on program and project performance is the impact of organizational qualities. And again, there's some really nice advice for this from the COSISMO model. You know, the better your organization is in terms of team cohesion, team capability, the continuity, the experience of those people in those teams, the process capability, your ability to coordinate across multi-sites, the better all of these things are, the more effective and efficient your overall organization is. So again, if you haven't prepared sufficiently prior to contract, setting up your organizations, if you try and set up your organizations after contract, And especially if you've got all of those assumptions that you've had, which have been unresolved, you're going to have a really hard time. Because this organization leads to firefighting. And again, there's this nice multiple cause and effect diagram from the Guide to Lean Enablers. If you haven't read this particular piece of work, I'd really recommend it. And as Bogdanov said back in 1917, a disordered whole is practically less than the sum of its parts. Within the context of the International Society for System Sciences, we've been doing some work looking at what we call general system pathologies. And these are the kind of pathologies that we see every day in our lives, in our programs, in our projects, at home, at work. The arrangement of the pathologies is particular, and I won't go into the details of how these were defined, but there's quite a bit of scientific work behind this. And what I'm showing you now is a diagram which explains how those pathologies occur. And what we have in terms of the red arrows are anti-systemic pathways which drive those pathologies. The ovals represent what is known as transformational powers. They're the drivers of change in all human activity systems. I'll just focus on the center, which is the political power, because the political power is essentially the power which everything else revolves around. Yeah. So we've got a pathology just slightly to the left, no vision of the future situation, and that is driven by reluctance to change, to retain the establishment. We have manipulation of information, hiding, downplaying the consequences, benefits of the parts, not the whole, which leads to the wrong direction, manipulation of relationships, blame the other. These are anti-systemic pathways. And one of the roles of systems thinking and the systems engineer is to promote systems being systemic, and the positive pathways are shown here. All of these pathways have behind them various different heuristics from numerous works of systems thinking from areas like the Waters Foundation, the School for Systems Change, and many others. But what we've done is we've organized all of those heuristics within this overall construct. Again, if we look at the political center, we resolve the pathology of no vision of the future situation by giving voice to future possibilities. We resolve the issue of not seeing the connection flow of causality through planning ahead. Wrong direction is resolved through taking ownership of issues, and lack of information, knowledge, and appreciation is countered through the engagement with stakeholders. And we have this cycle of knowing why, knowing what, knowing how, and the establishment of wisdom in this overall flow. Now, when we apply systems thinking, we turn that original diagram from the Guide to Lean Enablers on its head, and now we look at things from a more positive perspective. So smart acquisition and contracting practices leads to effective planning, which leads to projects that enable good and profitable business. And we can analyze each of these arrows in terms of the systems thinking, the positive pathways. We could also look at them in terms of the negative pathways. That work hasn't been done yet, but it's certainly something we could do. We've also done some work looking at the actual work products of systems thinking. So when you do systems thinking, indeed, when you do systems engineering and you apply our systems engineering processes, these are the actual work products. So when we look at the center, again, we have vision, mission, and objectives, which are part of business and mission analysis. We have planning, which is obviously part of the planning process. We have accountability, which would be part of the decision management process, I would guess. And we have the laws, the policies, and the conventions, which reflect the societal needs and expectations. So all of these different things are the subject of those positive pathways that I showed you, when you're following those pathways, these are the things that you concretely produce. So this would be something that would be worth looking at in terms of our systems engineering processes and how they map to these individual things. I'm going to move now more into the realization of technical management and how you'd actually plan for it and how you'd actually do it. And I'm going to draw on the work of Bud Lawson, who was one of the authors of the lead authors of the ISO 15288 processes originally. And what he was doing as one of the things he did was he looked at the OODA loop, observe, orient, decide, and act, and the plan, do, check, act loop. One is a strategic loop, and one is a tactical loop. And what he did is he brought them together in terms of that overall diagram on the right, where the act of planning strategically was the act of planning from a tactical perspective. And when you bring those two loops together, you have the potential to put in place continuous situational management. This, by applying this is this that makes you strategic, agile, lean, and responsive. This is the essence of essentially systemic project management or technical management. So many of you, I think, are familiar with the SEMP. Now, one of the things I'm advocating is that instead of calling it a SEMP, we call it a technical management plan, because what we're essentially doing is we're managing the technical processes. And if you look at our systems engineering handbook, it talks about technical management processes, and this is what we're realizing through the technical management plan. And there's a technical management content which relates to particular thought processes, and the areas under consideration. And those areas under consideration, they map really nicely to the different features of the co-systemo model. So the thought process is starting from the bottom, understanding what the purpose is, analysing the stakeholder needs, analysing their key concerns, assessing the scope of the task, assessing the complexity of the risks, defining the technical strategy, defining the scope of each technical iteration and phase, defining the work products, and you get into more and more detail of the main parts of the technical management plan. And when we look at again at the OODA loop and the plan, do, check, act loop in correlation, we're observing who are the stakeholders, what are their needs and concerns, making sense of the information, what's the purpose, observe, orient, decide, act. And then you've got the plan, do, check, act on the right hand side, and going up the left. And all of these individual things that the technical manager needs to be doing essentially all of the time is keeping all of these things in alignment. It's continuous situational awareness. And on a day-to-day basis, what you're doing is you're keeping an eye on the progress metrics, keeping the team focused on generating value, ensuring all of the interdependencies are respected, promoting collaboration across the teams and the disciplines, and being visible, proactively dealing with questions and issues. And the technical management plan is not just a document that sits on the shelf and is never looked at ever again once you've delivered that to the customer or you've done your kickoff. It's in a modern digital way of working. It is essentially your digital construct for how you set up the environment for your team and how you manage them. That continuous situational awareness is really important, because if you end up on a project where things haven't been done right, or you discover that things haven't been done right, or that certain assumptions have really turned out to be significantly false, you may end up in a situation where in the rush to initiate a contract, understandings have been glossed over, the startup may have failed. You're starting to realize that if you continue on your current path, your overall design will fail, and your implementation will fail on the current trend, and you will end up with an overspend which looks something like this. At that point, if you act here, you may have an opportunity to revisit your architecture, revisit your solution, revise your understanding of the problem, put in place a right design, and prepare for a right implementation. By spending that extra effort at the right time, you may have the possibility to mitigate the overspend. But the longer you delay in recognizing the situation you're in, the worse the result will be. And consequently, your ability to improve it. So I've done pretty well in terms of time. I think I've got another 10 minutes or so. So what I'll do is I'll go relatively quickly through some of the bonus slides. So I talked a little bit about heuristics, and heuristics are part of the empirical domain. Um, this is where we learn how to do stuff by experience. We won't necessarily have the understanding of why um, those heuristics work, but we know that they work. We know through experience that they work, and that can lead to new inspiration and starting to wonder, why does that happen? Um, and another route to conceptualization is pure thought. And when you build concepts together, you build theoretical models for explaining why, and then from those theoretical models, you can derive scientific-based principles which can then be operationalized and put into practice. So heuristics are essentially principles which have not yet been grounded in with a theoretical underpinning. And the progress of science is a continuous process of of developing new models, developing principles, getting better understandings of why, and then putting those things into operation. And there's a feedback and a feed forward. In terms of system science, there's two dimensions of system science. There's universal knowledge about nature's transversal patterns, um, and this allows us to understand the context for systems, the systems themselves, which are entities, the mechanisms which realize those entities and lead to emergent properties. And that overlays with knowledge about how we engage with systems. And I showed you some of those diagrams earlier about the positive and the negative pathways. That overall construct, that general human activity system, is a system in its own right, and is in keeping with nature's transversal patterns. As we go through our engineering, we go through a process of conceptualization, gathering information, developing knowledge, which we then represent in our architectures. And architectures are essentially constructs for understanding and appreciating what something is. The process of design is then working out how that architecture is actually going to be achieved, and provides the principles that are applied in the production of assets and making those systems real. Complex endeavors are best served with systems thinking. So we all know that within our teams, it helps to have a diversity of people and specializations, and also the traits and innate abilities of the people. Some people are better in the why domain, some people are better in the what, some people are better in the how, and some people are better in the actual implementation of the operations. That's just a natural way that our organizations and our people have developed. I've got a slide on conceptualizing, architecting, designing, and realizing. I've done some analysis of the PMBOK issue 7 and 6. PMBOK has changed from 6 to 7. It's moved away from what I would say is a more reductionist approach based on process groups and knowledge, and has moved to principles and domains, which is really interesting. So I think that what's encouraging is that PMBOK is taking a more systemic approach, which I think will lead to more opportunities for collaboration with project management, with systems engineering. I've compared the heuristics from how big things get done, which was in that book, and also the principles which are described in the PM guide. And when we look at the placement of those heuristics and principles, we can see how they map to the transformational powers, the different domains. We can also see how they map onto the positive pathways and the negative pathways, and how those different principles contribute to the production of these different aspects of work products. I've done a similar kind of thing looking at the INCOSE SE principles as well. So principle 1 and 11, they map quite nicely onto the political power, and that relates to full life cycle management, promoting holism, which is in the social domain, appreciating complexity, which is I think it's on I can't remember. This is the theory area, needs and purpose, systemic understandings. So you can see how I've mapped them onto the principles, onto the positive pathways, and their contribution to resolving the negative pathways. So I think that probably brings me up to the 40 minutes.
Thank you, Gary, for a great presentation. I'll now look through the questions that have been posed by the audience. And for anyone who arrived late and missed my introduction, if you have a question for Gary, please could you write that in the Q&A, and then we'll work our way through the Q&A. So the first question I have here it goes back to that Venn diagram between program management and systems engineering and the technical management overlap. As I recommend using the figure 5.4 of the new INCOSE SE Handbook Edition 5 that has been produced by the PMSE Integration Working Group. I think it's the there that you're.
Yeah, it's that one. Yeah. There's an expression, you all know it, all models are wrong. Some are useful,
So, next question. To what extent do you think handling information effectively is a fundamental enabler to technical engineering management?
Oh, that's a good question. Yeah. So, I'm going to, okay. So information, yeah. So knowledge is organized information, and information is associated with events, the provision of data, messaging. So information obviously plays a key part in our knowledge base. Information is absolutely vital. I think the point I'm trying to grapple with and communicate on is that you can be in receipt of an informational event, but unless your knowledge structure is capable of receiving that information, then the information will basically just fly over your head, and it will have no impact. So there's that key mechanism of recognizing what information is valuable and what information is not, because we're becoming more and more overwhelmed by data, and not all of that data will have valuable meaning. But also, it's also important to understand what data is important and what isn't. And I think that this is, one of the potential benefits of AI as an adjunct. AI will help, but I still believe and hope that having a human in the loop adds additional value. I hope that helps answer the question.
So I'm going to put a couple of questions together here. They're from the same person. Isn't the proposal, the contract, and the execution a system of its own? Seems like they're independent and can be construed as a system of systems and should be considered holistically. If the complexity arising from different cultures and perspectives and motivators are considered in systems thinking, don't they increase risk?
Yes, if those things are not considered as a whole, then it does lead to an increase in risk. The other thing I'd say about that is diversity in thinking is both potentially beneficial, but it's both beneficial but also potentially a problem. There seems to be a sweet spot in terms of diversity and alignment. Diversity is the source of emergence, but it's also the source of chaos. So there is a sweet path, and I think David Long talks about this. You know, when he talks about systems engineers in terms of their what's he call it? I can't remember. It's the systems engineers are weird. Yeah, that they're able to both think deeply but also think abstractly, and they have many traits which go, you know, that I can't remember the word. Can't remember the word, but it's. I think you guess. I think you can guess where I'm coming from. Yeah.
The sort of T-shaped engineer.
Yeah, it's more than just T-shaped. It's you know, we are weird in systems engineers are weird in terms of they can both think broadly and yeah, as you say, deeply and also broadly. Yeah.
So there's a question here, but I think it was asked before you'd actually got on to showing the various mappings. But I'll ask the question anyway. Have you mapped the system thinking outputs to the systems engineering process flow and framework, also to outputs that can be gathered out of model-based systems engineering type tools? I think the answer is yes.
Yes, I have done that. One of the things I'd really like to do. So within that general human activity model, there are 24 reversible pathways, essentially, with a positive pathway and a negative pathway. And if we were to look at that pathway in the same way that a chemist looks at a reversible at a reversible reaction, what we can do is our understanding of the concepts, the principles, the methods, the tools, the processes which are applicable to that particular space, that would then give us the tools and the wisdom to be able then to better manipulate the reaction so it becomes more positive. I don't know if many of you have got familiarity with chemistry, but basically in a systemical reaction, you've got, you know, A and B, which makes C and D, and you can change the circumstances so that you move more to the right hand side rather than the left by manipulating, for instance, the environment or the temperature, or, you know, and we could do the same kind of thing with systems engineering, you know, because our job as systems engineers is essentially to promote systemicity and to downplay and to mitigate those negative anti-systemic pathways.
So, question about rich diagrams. So you've presented a lot of information diagrams. Has there been any attempt to drive out concept models that go across all of those domains illustrated?
Yes, there has been. Yeah. So on this diagram that I'm showing at the moment, for instance, if you could imagine, as we go through the life cycle of knowledge development, you have concepts on the far left hand side. So concepts are more abstract. When you bring concepts together, those concepts then start to form theoretical models. Theoretical models can then be utilized to create assets, and those assets then play a role in the real world nature and society. And what we've done in terms of the concepts, drawing on the work of David Rousseau and his collaborative partners, we've identified 6 different categories of abstract systems concepts. We have identity and togetherness, we have behavior, cycles, capabilities and purpose, value and qualities, and experience and consciousness. Those 6 different categories are groups, which then lead to subcategories, and those subcategories relate to, those subcategories are essentially the concepts and the words that we use in our communication when we talk about systems.
Sorry, I was muted. There's another question here, and it's from someone who has a lot of experience in their career, and says the enduring question is, how do you get non-true systems engineers to value and use these techniques? Too often, as you say, the rush is to do versus think and understand first.
Well, that's the $1 million question, isn't it? Yeah. So one of the things that I haven't yet conquered is being able to pitch systems knowledge and systems understanding at the right level to the right level of audience. It's really so. Ray Eisen describes this quite nicely. So Ray, who works at the Open University, he's come across this concept of what he calls system sensibility, and there's a range of what he calls system sensibilities, and we might say that systems engineers are more towards the top end than the bottom end, and it's all about communicating in the right way to the right audience. George Mobus has also done some work looking at I think he calls it it's sapience, and what he explains is that because of the way humanity has evolved, we're actually not that good, believe it or not, at thinking ahead. And even if we do think ahead, we tend to make short-sighted decisions. And I don't know. I think that one of the things we really need to do, again, left shifting, because left shifting is often the thing to do. I think the answer to this situation is really left shifting, such that we stop teaching kids about facts and we start teaching kids to think again. And bringing systems thinking and system science into our education, I think, is really important, because there's the expression, you can't teach an old dog new tricks, and maybe that's part of the problem. Yeah, it's certainly a challenge. Yeah. But I think one of the things which can help is showing those kind of diagrams which show the trends over time, and essentially explaining, if we don't do something different, it's just going to keep on going the way it is. And you look at climate change, and all the various COP meetings. Despite, I don't know, 25 different COP meetings, the trend is still continuing the way it has always gone. So unless we start doing something differently, we shouldn't expect anything different to happen, if we continue those same patterns. So I have found that being able to show trends, um, to those stakeholders does help. But you've got to have the opportunity to actually make that presentation in the first place, and that in itself can be a problem.
So there's a question here, and I think you've covered the relationship to lean here, but any thoughts how lean and Six Sigma align with the concepts shown today?
Um, I can't say that I'm I'm aware of Six Sigma, but I can't say that I'm familiar enough really to comment on it. I know that in the guide to lean enablers, there was quite a lot of work done looking at the relationship of lean and the systems engineering processes. So that would be my go-to place as a starting point if I was to do that analysis. So sorry if I'm ducking that question.
Okay, there's another question here, and it must be from a very dedicated systems engineer, because he said you proposed the following terminology: systems engineering, technical processes, technical management processes, and technical management plan. What about systems engineering technical processes, systems engineering management processes, systems engineering management plan? In other words, the program gets quite downplayed. What's your feeling about that?
Um, well, so one of the things I am concerned about is that systems engineering becomes yet another silo. Um, so I tend to, although I am a systems engineer, and I completely value all of the work we've done in terms of systems engineering, absolutely. But when I'm talking with other people outside of systems engineering, I tend not to use the systems engineering label. So, for instance, when we're doing development, I refer to the technical processes of doing development. I talk about, development processes, or I talk about manufacturing processes. Now, the manufacturing processes, the support processes, the development processes, and you could even say the cell processes, they're all supported by technical processes. Um, so, the way I would advocate things is that, I would like, just let me share my vision. My vision is that when we do all of that, when we do essentially engineering, the way that we do engineering is it's all about applying systems engineering. What I would be concerned of, for instance, is you have a set of engineering processes, and then on the side you have a set of systems engineering processes which are not, or they're almost like a silo sitting on the side of the rest of the engineering processes, when the reality is that everything we do should be systems engineering. And when we look at our ISO 15288 processes, you've got the processes related to the overall business, you've got the processes related to the project management. All of those processes are systems engineering processes. Systems engineering processes, just like systems, are everywhere and everything. That's the essence of it. So I was just sharing a few of my views on systems engineering. Systems engineering is everywhere and everything, just like systems.
So I think we've got time for a couple more questions. Next one, any thoughts or plans to also map or analyze the INCOSE systems engineering competences from the systems thinking, systems science perspective?
That's a good idea.
And then the final one, your slide, complex endeavors are best served with systems thinking,
Oh
showed
yeah.
what, how, why, and establishing common wisdom domains. You
Yeah.
suggested these are the 4 natural domains of systems engineering specialization. We're trying to determine if systems engineering needs to specialize in our organization. Have you seen specialization into 4 domains in an actual organization executing a project? And if so, how did it work? What were the 4 specialties you called? And did they decide to change it?
You faded out there, I'm afraid, Andy.
Okay, so I'll try again. It's on this slide, and in this person is saying we're trying to determine if systems engineering needs to specialize in our organization. Have you seen this specialization into 4 domains in an actual organization executing a project? And if so, how did it work? What were the 4 specialties called? And did they decide to maintain that structure moving forward or change it?
Yeah, no, I've not seen it. I've not seen it done that way. I've seen these 4 quadrants naturally broken up in terms of different phases. I think, I mean, what you could do is you could, I mean, whenever you just make a distinction, you're always drawing the possibility of creating a silo, and obviously what we want to do is we want to ensure that you do have an overall team. Um,
Okay,
yeah,
so I think we've
it,
come to the end of the questions there then. Could you go on to the next slide in the pack,
sure.
please? And thank you, Gary, for a great talk, and thank you to the audience for your question time. The next slide shows upcoming schedule, and unfortunately for the next 2 months, we don't have anyone scheduled yet. We do anticipate scheduling webinars in February and in and additional webinars will be offered typically on the 3rd Wednesday through 2024. If you'd be interested in presenting an INCOSE webinar, please let me know. And please note, if you go to the website shown here, you'll see more information about the webinar series, including a way to view the last 169 webinars, and soon this webinar as well. Next slide, please. The INCOSE International Workshop will be held in Torrance, California on the 27th of 30th January 2024, so not very far away at all. Here's the website for the workshop. Registration is open. Click the Attendees tab to register. Next slide, please. As mentioned earlier, you can now claim 1 PDU credit towards your systems engineering professional recertification by attending this webinar. You may also claim this credit retrospectively for INCOSE webinars that you have attended and where attendance meets the qualification requirements. Next slide, please. I'd like to express thanks again to Lockheed Martin Corporation and Spec Innovation sponsoring the 2024 INCOSE webinar program. Thank you again.